Well, good afternoon. We're at the stretch, and I'd like to thank Miter Ingenuity for adding this topic to the summit. Um, I consider minimum wave as a critical, ingredient to fully realizing the true promise of 5G. What that means is, from a consumer experience as well as the demands of applications to include industry and critical infrastructure. And I'm happy to be joined in the panel by three technical experts, around radio access network, starting with Amitabha Ghosh from Nokia, Jisung Oh from Phytunes, and last but not the least, Javed Khan from Rakuten Symphony. And I'm going to ask each one of them to introduce themselves in the same order. Amitabha, you start.
Hi, glad to be here. I'm Amitabha Ghosh from Nokia Strategy and Technology, and I'm part of the Nokia Standards.
Thank you, Jerry. I'm Jisung Oh. I'm CEO at Phytunes. Phytunes is a new startup founded in 2020. I'm very happy to be here.
And hi, Jerry. I'm glad to be here. This is Javed Khan. I'm a director at Rakuten Symphony and working in 5G product management and business and product strategy.
Well, thank you all. Well, I think we have to meet expectation. Somehow, this has been advertised as very exciting, multiple times in the course of the summit so far, right? But my objective here is to leave the audience with a good understanding of what millimeter wave is and how it's uniquely positioned, right, to provide for the bandwidth, the capacity, performance that a lot of the application services, that we talked about so far, need. And if you go to the next slide, Billy. Okay. So what you see here, right, is an outline of what we're going to talk about, starting with understanding the characteristics of millimeter wave, especially vis-a-vis the other band, low band, mid band, you can see on the left hand side, and millimeter wave as part of the high band, starting with 24 gigahertz onwards. And I'd like to take the discussion to what use cases do we have today, and what use cases do we see in the future, noting that there is also an evolution both on the technologies behind the millimeter wave and the spectrum as well. Now, my panelists are kind of like really technical, but I'll take them kind of like, out of their hat to help us, understand, where the global adoption is as far as, how the device ecosystem uptake, taking place for millimeter wave. And we'll go look into, areas or challenges, that we see as far as the deployment of millimeter wave and what kind of solutions or mitigations are in place. We'll also talk about wireless backhaul as an enabler, and lastly, again, taking them out of the comfort zone, see how or talk about how we can monetize millimeter wave, not in the dollars and cents, right, but how millimeter wave can uniquely address additional uptake from services that we have today, as well as what kind of like how it enables new market, as well as alternative to other technologies. So with that, I am going to jump right in. So uh, and by the way, I will have lead questions, but I encourage my panel to be interactive, in terms of our discussion. Okay, so let's start with what is millimeter wave. What is it? What is its unique characteristics relative to the band spectrum? And and I'd like to also touch on how that millimeter wave has evolved. in the course of time. So let's start with you, Amitabha.
Yes, thank you, Jerry, for this question. So, as you know, that favorable spectrum, lower band spectrum, is limited, whereas the subscriber traffic continues to grow at an exponential rate. So, what is the advantage of millimeter wave? So, in millimeter wave, we have wide swaths of spectrum starting from 28 gigahertz, 39 gigahertz, 47 gigahertz. So, that is the advantage. We have wide swaths of spectrum. We can employ millimeter wave techniques. We can do all-in-one base stations because because if you want to maintain the same aperture, you see, you can do that. And then, but what are the disadvantages? The disadvantages is the propagation distance is short. You see, in a dense deployment, you can have 250 to 300-meter IST. You have huge penetration loss, so there is no penetration, so you can't cover inside from outside or vice versa. And then there is body loss, or you can blockage. So if you have a car, it will block the signal. So there is particular way in which a millimeter wave signals can be deployed. So in summary, millimeter wave characteristics, it has huge swaths of spectrum, it is adaptable to narrow beams and beamforming technology. You can do all-in-one base stations, but it has huge penetration loss. You can't cover inside from outside or vice versa. And it has blockage, heavy blockage loss. So to make millimeter wave successful, you have to, so there are various use cases we can talk about. And what, so in a mobile scenario, you need densification techniques, but the current deployment of millimeter wave is for EMBB with fixed wireless access. And is that sufficient, Jerry, or gives a good introduction?
Yes. Anything you want to add, Shinsuke?
Yeah, adding to Amitabha's comments, I would also like to emphasize that the millimeter wave spectrum allows a wider bandwidth, offering higher data rate, and thus enabling lots of unique use cases that has never been achieved before. But still, as Amitabha mentioned, that there are a lot of changes. But nowadays, thanks to the advance in CMOS RF technology, we can make a pretty good, power amplifier with good efficiency, so that now we can kind of build up a commercial product to embrace the millimeter wave spectrum. But still, there are some more, technical barriers that we need to overcome. Beamforming, it has been introduced for the commercial use of a millimeter wave, but it should be enhanced. And also, we need to think about how we can solve the indoor reception problem as well. So there are lots of room to look at in this area for us to finally commercialize this millimeter wave technology.
Okay, so with the limitations that we've heard, considering the strengths of what mmWave can provide, Javed, therefore, it's logical, to see mmWave as addressing, certain unique scenarios and use cases, right? So that being the case, millimeter wave at best could be seen as complementary to the other, bands, right? Can you elaborate on that?
Yeah, exactly. So, as Amitabha mentioned, right, millimeter wave, brings in a lot of, it got a huge bandwidth that is unparalleled, right, compared to the narrow band that we see today in sub-6. And so in that, for that reason, it's very attractive because of the, potential for high capacity layers. So, and that is exactly what has happened. The initial deployments of millimeter wave in the US, and South Korea, or in Japan, they focused on basically capacity expansion. And because millimeter wave, because of its propagation characteristics, right, it behaves more like a small cell, because in urban and dense urban deployments, you can't really get the propagation. And so you can, typically what has happened is we've deployed these like small cells in urban and dense urban areas with typical intersite distance of 150 to 200 meters. And what has happened is, for the initial deployments, they've since ENDC, which is EUTRA NR dual connectivity, was prioritized. A lot of the deployments have been where these millimeter wave radios have been deployed at LTE cell sites in dense urban areas, and essentially they act as a secondary cell, providing capacity, and complementary to the low band, narrow band control plane. So what we've seen is, you have an LTE carrier, let's say of 20 megahertz, and the user gets in the coverage of these millimeter wave radios. They get essentially up to 400 megahertz or even 800 megahertz of bandwidth, possibly by adding this millimeter wave carrier as a secondary carrier. So that certainly boosts the total throughput that the user is able to perceive, as long as they're in the coverage of these millimeter wave radios. So what we've seen is that a lot of these deployments have been in urban and dense urban areas, similar to how small cells have been deployed to add, basically to provide coverage and, more importantly, capacity. Now, those have been, so with ENDC, you can get mobility, right? You can have a cell phone with the millimeter wave capability, walk around, in a downtown area, you're in the coverage of these radios, outdoor radios, and you can get throughputs up to above 2 gigabits per second on the downlink. And uplink, you can get up to 700 megabits per second, for example. So it's pretty dramatic increase in capacity that you can see and throughputs that you can see. And but the millimeter wave has also been targeted for fixed wireless access, where you have apartment complexes or residential areas, and you can put up a millimeter wave radio because of the bandwidth that is available, where you can a lot of users can share, be supported by that, by the millimeter wave spectrum. Obviously, initially, since dual connectivity was supported, you also need, the operators also need to provide LTE carrier, and then now millimeter wave standalone architecture, where you can just put up a millimeter wave radio with standalone architecture. It does not require a corresponding LTE band to be available, and so now it makes it much more easier to do fixed wireless access. And there's been technology where the test been done where they've increased the coverage of fixed wireless access by higher power radios, and also line of sight coverage.
And
Uh, yep, Amitabha.
and to add to that, the other applications of millimeter wave is for enterprise indoor deployment. So you have a factory floor, right? And you can deploy a millimeter wave standalone system over there, which will give you high throughput and enable applications which was not thought of before.
So with that, Amitabha and others as well, you guys can pitch in, right? Is there anything inherent in millimeter wave that it's well suited for, let's say, low latency, demands of the application and the environment, as well as, let's say, high precision positioning? Or
Yes,
is that more a
so
function of the deployment as well?
well, we are looking at positioning in release 1718, and more the bandwidth, the better is the positioning accuracy, right? So we have all these positioning methods, TDOA, TOA, and we now have carrier phase-based positioning method, which are being investigated in release 18. So if you want to increase the positioning accuracy, it is inversely proportional to the bandwidth. So larger the bandwidth, the better is the project. In that way, we can leverage millimeter wave for higher positioning accuracy.
Okay.
And
And Javed, I'll add real quick, right? So with Verizon, we brought our ultra wideband millimeter wave experience, right, in venues like NFL stadiums. And if you look at that, you have density of, you know, uh, sports fan, live. Uh, doing a lot of video streaming, right? And we brought the multi pane immersive kind of experience, right? So what that really demands is high capacity, high bandwidth, and being able to with low latency handle a sheer number of users, right? And that you can take in addition to fixed wireless access and some kind of like high density hot zones, right, from a consumer mobility type of experience. Um, so now I'm going to switch now to um, do we see millimeter wave still evolving within standards, and what has happened since release 15 and release 16 on it?
So I can. So Javed, you want to take it, or I can
no,
take
yeah,
it?
go ahead, Amitabh. I think
Yeah. So currently, so millimeter wave was introduced in release 15, right? Because nobody thought that millimeter wave will be an access technology before everybody thought it will be only a backhaul technology. But one of the key things is that small cells are projected as a solution to improve capacity, but have failed to gain traction, whether it's sub 6 gigahertz or millimeter wave. Millimeter wave is ideally suited for small cells, and where site acquisition continues to be a challenge. Acquiring access to meaningful street furniture is a challenge. Access to power is achievable through this lamppost. And finally, wired backhaul or fiber connection to each of these lampposts is problematic because it involves cost, especially in the US. So, to make millimeter wave densification possible, you have to look at the deployment, and you have to look at wireless backhaul techniques, which are integrated access and backhaul, where you can take the access spectrum and make it TDM, where you can devote some of it to backhaul and some of it to access. And that has been standardized in release 16 and 17. Uh, that has been standardized in release 16 and 17. In the other techniques which are being used is dumb repeaters or smart repeaters, which but we have not seen traction with respect to integrated IAB, what we call it, which has been standardized because of the very reason that nobody is willing to build the IAB nodes, which has mobile station kind of functionality. But to make densification possible, you have to have wireless backhaul, and that can be achieved in the IAB smart repeater, dumb repeaters. So without that, it is very difficult to achieve densification because you can't draw fiber at each node because of the sheer cost.
And maybe I can add to that. I totally agree with what Amitabh just said. What we've seen in our deployments in practical cases, majority of the deployments are at the macro cell sites, right, on rooftops in cities, precisely for that reason, because there's no backhaul or fiber available, or there's not enough infrastructure to host this on light poles. Although we've done deployments on light poles, but a majority of the deployments are on rooftops, co-located with LTE macro radios.
Yeah, so that's true. With the plenty of available bandwidth in millimeter wave spectrum, millimeter wave can be easily employed as an out-of-band backhaul as well. So which means that
Yes.
it does not interfere with the actual 5G network in use. So we can easily well coordinate the network deployment using a wireless backhaul.
Yeah, that is a good. So we can have out of band backhaul at, say, unlicensed band, say 77, 70 gigahertz, 140 gigahertz. But then you need two radios, right? We have a backhaul radio, and IAB is a simpler because you have one radio which can do both backhaul and access. But here you need two radios.
Another way we've tried to solve that problem, or not necessarily solve, but kind of mitigate some of the problems with the bandwidth requirements, right? Instead of transporting the front haul traffic, which can be, multiple gigabytes of, capacity requirements or bandwidth requirements. One of the things that we've done in our network in Japan was to deploy radios which have the lower level RLC, MAC, and PHY in the radio itself. And so essentially the radio is like what is called option 2 radio, where the traffic that has to be now kind of sent back to the core network is the F1 interface, what is called the F1 interface in the standard, which reduces the bandwidth requirements. But you still have this problem of lack of fibers itself, because you still need like a 10 gigabit link for that F1 interface as well. And so that's why you're still like limited to these sites which have that fiber.
Okay, so yeah, I think we got into the topic now of challenges that we see in deployment, right? Starting with densification and mmWave. Uh, so, do you have anything to add as far as what we see as barriers to adoption? In general, in the use of mmWave.
So what I see, if you want to do this in an environment, if you have dense deployment, you need to have the base station. You have to install the base station in such a way that it has visibility and user have visibility to multiple base stations. So take city of Chicago, you put the base stations in the street corner in such a way so users have visibility to multiple base stations. So if one of the base station gets blocked by body blockage or traffic, you can have visibility to the other base station. So you have to sort of um, uh, deploy in a smart way so that you have visibility to multiple base stations. So that's one of the techniques. And with integrated access and backhaul, you see what you can do. Initially, you can deploy without fiber, right? So what we have seen, we have done studies of IAB. What in the initial stages when the traffic is low, you can have these IAB nodes which you can just plop down without any wired connection. And then as the traffic grows, you can convert these IAB nodes into wired backhaul nodes. Because with IAB, we are just borrowing capacity from the access link, right? Now, when the load is light, it is fine, but these IAB nodes can easily be converted into backhaul nodes by just plugging a fiber connection as the load gets higher. So
I also pointed out the challenges from the user device perspective, because to have a good and stable 5G millimeter wave 5G connection, we also need to think about the user devices, which is usually driven by the battery, right? The battery limited devices, and then the signal can be easily blocked by the human bodies, right? And then also there may be a case that while receiving the 5 millimeter wave 5G signal, the temperature of the device can goes up. So it may be a little bit kind of uncomfortable to the user. So to have a better network configuration or deployment, the distance between the access point and the user device should be quite short, so that we can easily receive the signals from the access point. Otherwise, for the uplink scenario, the power the drainage will be used and it will hinder the use of the millimeter wave of 5G. Yeah.
Okay, I'm going to pick a question, one question from the chat here, because that's tied to the question I was about to ask you, Jisung. Um, how can millimeter wave work indoors? How can millimeter wave work with Wi-Fi indoors? Right, but the question that I think is tied to what I was just about to ask you is what will be an efficient way of providing millimeter wave signal indoors? So if you can talk to that, that'll be great.
Yeah, so when we think about the outdoor millimeter wave access points, I mean, it is quite obvious that the signal cannot be reached indoors, right? So that has been known as a kind of bigger problem, the indoor reception, characteristic or property. So nowadays, the most of the new buildings are kind of has a very thick walls or tinted windows, which makes it even harder for the millimeter wave to like get in. So we definitely need to have a repeater type of things or a DAS system for the millimeter wave 5G as well. But we can also think of a smarter way of distributing the millimeter wave 5 signal inside the building or inside the house by leveraging the existing wireline infrastructure, such as a coaxial cable or Ethernet cable that we already have in our building or in our houses. That's the new area that and also help us to make an easy and fast deployment of indoor millimeter wave.
The other solution can be, which I agree with Jisung said, is that we can have a separate system, a standalone system, like in a factory, which is indoor, right? So we can have a separate millimeter wave system inside. Now, to bring the signal from outside to inside, there are a lot of research going on re- intelligent reflecting surface, IRS, or reflecting intelligent surface, RIS.
Yes.
So what we have seen, you can mount this RIS. It's a passive RIS where you can use this to bring the signal from outside to inside. Okay, so there are a lot of solutions on how indoor coverage can be provided using millimeter wave. Have a separate millimeter wave system, or if you want to bring the outside signal to inside signal, you have to put some sort of things like the race, or you can have a sort of a converter where you put this outside the window, convert the signal to sub 6 gigahertz, and then distribute it within the home. So like the fixed access solution.
Yes, true. And then the better solution should be easy and fast and cost-effective deployment, right? And then also usually introducing those indoor solution, requires a little bit more latency in the signal distribution. So we also need to think about the latency while we are redistributing the signal inside. So I believe there is many ways, but we need to be focused on a very, you know, economical way of redistribution of the indoor 5G signals.
Jared, I believe you were about to say something before I asked the question.
Um, well, I was just going to add that we've done deployments of indoor millimeter wave radios where you can get a lower power, lower EIRP radio indoors. It comes with its own set of challenges, but with low power millimeter wave coverage indoors, you're still able to get the benefit. Similar to what Amitabha said, right? It could be again these option two type of radios where you can distribute them on a floor, in corners, and route set up a system either connected to the public PLMN or as a private network, right, inside a factory or on the shop floor. So we've done indoor deployments, and I think it has worked well.
Mhm.
All right, so let's switch now to the use cases, right, that we see today and in the future, for millimeter wave. We kind of like touch on that in the course of our discussion so far, but since this is the headline to the panel discussion, let's kind of like bring out and try to tie this into what we've heard as well, in the course of the summit so far. Who wants to start?
I can start and then uh, in terms of use cases, as we discussed earlier, the current use case or the use case that is more prevalent today is EMBB, essentially adding a capacity layer to existing narrowband. And then of course there is fixed wireless access that once we get standalone architecture support, that will become more prevalent. And then I think Amitabha mentioned earlier, in terms of latency, right? Because millimeter wave uses a much higher subcarrier spacing, 120 megahertz. It can be, it's suitable for industrial IoT type of use cases. Once we get device support and standards, they are still being worked, but there's a lot of interest in industrial IoT applications. With the massive bandwidth, you can do AR VR type of applications for medical use or for training and visualization, for and so on. And so, the large bandwidth coupled with its low latency, characteristics, it is a good band to use for certain applications in industrial IoT settings. And in terms of some of the use cases, again, in our consortium, in fact, where we are working on urban air mobility, for example, or UAS, millimeter wave could be a potential candidate for access. It is relatively a new band, not a whole lot of users on it, and it could be used for low flying UAS, in terms of maybe pointing the radios up to if you have this commercial service where they can provide the access to drones and urban air mobility, air taxis, for example, where they can provide both the control plane and the user plane, with this large bandwidths, it can provide a fairly good uh, I guess backhaul for users on that air taxi, for example, right in the future.
Yeah, talking about air taxis and thinking about vertiports, right? And what we've heard from NASA, and taking vertiport as kind of like a critical infrastructure, right? So I would think that that play very well in terms of what we could look at solving and run experimentation on, that will help make that happen, especially using millimeter wave in that scenario. So talking about that, there's also private network, right? So what could like anything that you can add, Jason, as far as use case scenarios, especially around private networks?
Yeah, sure. Yes. As Amitabh said that maybe the stadium use cases or factory use cases can be one of the private network. I believe it is really good application of a millimeter wave because inherently millimeter wave systems coverage is kind of shorter than the sub-6 gigahertz 5G, but we can still expect some sort of a security because the coverage is not that wide. So basically, the 5G is the first standard that can enable powerful industrial use cases, right? And then 5G's secure, robust, and low latency features encourage the enterprise to build its own private network. So millimeter wave 5G also has a lot of advantage in this private networks, and they can provide a more secure and dedicated coverage for the specific purposes and applications. And then still, the millimeter wave 5G product requires a lower upfront investment and a quicker deployment and more flexibility in placing the connection points around the private spaces.
Now, Amitabha, as we are preparing, right, you also raised the fact that the 57 to 71 gigahertz was added right into the millimeter wave. What kind of use cases do you envision being realized by that higher band of millimeter wave?
So, what my original thought is that there is this huge swath of spectrum, 14 gigahertz of spectrum in the unlicensed band, which we are not using. The 3GPP started addressing it. And so the thing is that more the spectrum, the higher the data rates. So, how can you leverage this unlicensed spectrum eventually? And so so there has been some studies that whether we need listen before talk techniques at this band, you see, because of the beamforming techniques, we may not use because in sub 6 gigahertz you need LBT mechanism to make the system work. But in this regime of 57 to 71 gigahertz, you may get away by not using LBT. So things are being researched in this area. But my thought is that we are talking about sub-terahertz, we are talking about small spectrum, but there is this 14 gigahertz of spectrum in the unlicensed band, which we should first use.
Okay. Uh, And just real quick, right? So if we look at where millimeter waves is used today, around the globe, um, can you briefly kind of like describe what the current state is in terms of adoption and availability of devices, including diversity in terms of form factor?
Maybe I can comment. So millimeter wave has primarily been used in of course in the US. Verizon, for example, has a lot of spectrum, and they're deploying there. Outside of the US, it's been primarily South Korea and Japan who have adopted millimeter wave. Again, as today, all most of the use case, in fact, all of the use cases are for EMBB, adding it as a capacity layer to ENDC type of deployments. But we will expect we can expect to see fixed wireless access also picking up, as we had discussed before. Devices, most of the devices or at least the focus has been on handheld devices which support millimeter wave. I believe chipsets would probably support both 28 and 39 gigahertz bands. And in terms of fixed wireless access, you would have these CPEs that would support millimeter wave for in the residential or from the in the on premises, and to support fixed wireless access. So those are the two kind of main use cases that are prevalent today, and there is device support for these bands.
And to add it, so I thought there was a question that the current 5G millimeter wave devices are based on non-standalone NSA because it is simply easier to upgrade for an operator which has an anchor carrier in LTE. So for new greenfield deployments for operators who don't have 4G anchor band, then the non standalone will come into picture. So there will be standalone devices eventually.
I guess that's just kind of like approaching time because I see a question of the chat. I think this will be the only question that we can take since we're going to be quickly running out of time here. There is no user equipment available today that supports millimeter wave for 5G in a standalone deployment. How are we going to support private 5G network industry for all use cases? So I think it's kind of like really relevant, right? I don't know if a chicken and egg. So can you quickly respond to that question as far as when we're going to see this being available? Again, the question was millimeter wave for 5G as standalone deployment.
So yeah, so it depends upon the UE manufacturer, so which I can't answer, but we'll see standalone deployment soon. Um, because as I said, for operators who are in a greenfield deployment, who doesn't have legacy LTE system, for them a standalone will be the only way to go with millimeter wave. But it will happen. It will happen.
But this is one of the challenges that we have in our test bed, right? Availability of equipment in order to do that. Now, to close, I'm going to ask each one of you, instead of like teeing up, the monetization, if you can kind of like just briefly, in your own view, right, how millimeter wave plays uniquely, right, as far as added value in enabling all of the application services that we have, in particular, for enterprise and industry use across the different verticals.
Um, Maybe I can go ahead. For I think we've touched upon this before, right? For private networks and for industrial IoT, using the bandwidth and the low latency that is achievable because of the 120 kilohertz subcarrier spacing, it will enable new use cases for sure, right? AR VR is certainly kind of the top of the list, but even the low latency capabilities would enable use certain use cases. I mean, that it still remains to be seen where it'll get what specific use cases it will adopt it, but the capability is there. So I believe it's just a matter of time before use cases, you'll start seeing practical implementations that use millimeter wave for in private networks and in industrial settings.
I would like to once again emphasize that the private and secure network should be achieved by the millimeter wave technology. And then, as we mentioned before, that the manufacturing facilities or hospital, and then the subway on the airport area, those are the good application areas. And for verticals, then we can deploy the millimeter wave in a controlled way, so that we can promote the millimeter wave for a better use of a network, a resource, and environment for our everyday lives.
So, Amitabha, if we don't use millimeter wave, do we have any other option in this?
Well,
Con-
I will say, to meet the exponential demand in traffic, we have to use spectrum which is not sub 6 gigahertz, right? Because the spectrum is limited. So we have to go to millimeter wave to enable metaverse, right? Where it is high bandwidth application. We need large spectrum, 400, 800 megahertz of spectrum, so that we can offer hundreds of megabits of data rate to individual users, which can be done only millimeter wave. So although millimeter wave is not a mainstream technology, although it was introduced in release 15 in NR, but it will become a mainstream technology in next 5 to 10 years.
So it's important then that for OpenGen, to take millimeter wave in our test beds, encouraging the pipeline of technology solutions that will, unleash, all of what will be needed, with a targeted vertical, that we have prioritized. So on that note, I thank the panelists as well as the audience. Hopefully, you learned and had a better understanding of how critical millimeter wave for 5G, specifically. And I think that is the unique 5G user experience that's not only applicable in the consumer mobility context, but more importantly, with the enterprise industries and even defense establishments. Without which that we may have a problem. So with that, I'll close the panel discussion now. Thank you.
Thank you.
Thank you, Jerry.
Thank you, Jerry. Great.